Okay. Welcome to today's discussion. It will be physics paper 2. We are starting with the first question. I will read the question and then we shall proceed discussing on how to respond to the question. Okay. Question number 1, part A, Roman 1. Today's discussion states that asks you to state the principle on which Bernoulli's theorem is based.
Therefore, we need
you are asked to state the principle on which Bernoulli's principle is based. You are aware, or you know, that Bernoulli's principle relates the speed of a moving fluid, that is a liquid or a gas, with the pressure within the liquid or gas. So the law simply states that as the speed of a moving fluid, a liquid or gas, increases, the pressure within that fluid will always decrease. I'm just stating it, but the question wants you to say in what principle does this Bernoulli's principle base. So I said the principle itself states that as the speed of a fluid increases, then the pressure within that fluid decreases. And this principle is based on the principle of conservation of energy. The Bernoulli's principle is based on the principle of conservation of energy. That is the response to the first question, part A, Roman 1. Roman 2 of the same part says, why does the speed of a fluid, why does the speed of a liquid increase and its pressure decrease when the liquid passes through a constriction in a pipe? Why does the speed of a liquid increase and its pressure decrease when liquid passes through a constriction in a pipe? To respond to this one, we shall use the Bernoulli's principle. Since it bases on the conservation of energy, we can write pressure at point 1 plus a half density, velocity at point 1 squared plus, equals to the pressure at point 2 and added with half the density times velocity squared, but at point 2. So we can just think of the 2 points as as this. Let me consider this point to be point 2 and somewhere here to be point 1. So as you can see, the cross-sectional areas for a pipe at point 1 and point 2 are different, where you see the cross-sectional area at point 2 is pretty smaller than that at point 1. And as the continuity requires, we know area, say, at point 1 times velocity at point 1 must equal to area at point 2 times velocity at point 2. Which of course means that the product area times velocity must be conserved. And so if area is large, we expect the velocity to be smaller, and the value for velocity, say V2, must be larger to compensate for the smaller area at point 2. And so when the pressure is high, liquid velocity usually is low. When the pressure is high, and we expect for this case at this point to have a high, the velocity must be high, and so we expect here the pressure to be low. When the pressure is high, velocity will be low. Velocity here is high. We expect the velocity to be low, the pressure to be low. Here, the velocity is low. We expect the pressure to be high. So P1 is expected to be high because the velocity is low. At this point, we expect the velocity to be high or large, and so we expect P2 to be low. And so using this condition and taking it to here, you will see that the speed of the liquid, as the speed of the liquid increases, then its pressure will decrease when it reaches at a constriction. I repeat, when the velocity is low, pressure will be high. So at this point, we expect, because the cross-sectional area, according to the continuity relation, the cross-sectional area here is large, and so we expect the velocity to be low. And if the velocity is low, then we expect the pressure to be high. On the other side here at point 2, we expect, because the area is small, the cross-sectional area, we expect the velocity to be high. And if the velocity is high, we expect the pressure at that point to be low. And so we have used two ideas here. We have used the Bernoulli's principle, and we have also used the continuity relation. Where we have used the continuity relation to establish the relationship between the cross-sectional area and the velocity, and we have used the Bernoulli's principle to relate the pressure and the velocity. Okay, that is the response to question number 1, part A, Roman 2. Question number 1, part B, Roman 1. The question reads, if two ships are moving parallel and close to each other, they experience an attractive force. Why? I repeat, if two ships are moving parallel and close to each other, they experience an attractive force. You are required to explain why. Let me just erase this one. Part B, Roman 1. Say two ships are moving parallel and close to each other. You are asked, why do you expect the ships to attract one another? The idea is that as the ships go closer to one another, the hydrodynamic interactions take place. In a case that the cross-sectional area between them is getting smaller and smaller. And then, as we concluded from the first part, the last item of the question, as the velocity or as the cross-sectional area, of course, of the air that is between the two ships, because we are sure that there will be air movement between the ships. So if you consider the part, okay, or the place or the position before you reach the ships, it's like air was moving very freely because the area is quite large. But when the air reaches the point where the between the two ships, it's like the cross-section area between them is now small, and so the movement of the air will be very fast. That means the speed of the air will be very fast. And if the speed now gets very fast, the V goes up, the speed increases. It means, as we said previously, the pressure between the two ships will decrease. And if the pressure between the two ships decrease, we know there is a tendency of, now if the pressure at this point decreases, there is a tendency of air moving, being pressed to move towards the point of lower pressure. So likewise, if the pressure decreases here, there is a tendency of air moving towards the point of low pressure, and therefore the air will be pushing this ship towards the point of low pressure, and likewise the air on the other side will be pushing this ship towards, because the air is moving towards the point of low pressure, and so therefore these two ships tend to experience a force that attracts them together. So that is, in a nutshell, a response to that question. If I may put it in some simple writing, air velocity between okay, in the narrow gap, between the ships increases, the ships increases, and therefore the pressure decreases. The pressure decreases, and so the pressure on the outer surface, on the outer surface exceeds that between the ships, and therefore ships are pulled towards one another. So this is just to summarize what I have just explained. That was question number 1, part B, Roman 1. Let's go to question number 1, part B, Roman 2. The question says, an empty vessel is open at the top and has a horizontal capillary tube of length 20 centimeters and internal radius 1 millimeter that protrudes from one of its side walls immediately above the base. Water flows into the vessel at a constant rate of 1.5 centimeter cubed per second, and you are asked to find the depth of water. You are asked at what depth does the water level stop rising. Required to find the depth at which the water level will stop rising. Here we will use the Poiseuille's formula. We will use the Poiseuille's formula, that is part B. And before we apply the formula, let us consider just the sketch that reflects the question. So I can just assume it is as low as that, and I can just think of water, say, being released from somewhere, and so just consider this tank like having a height h. Of course, this height must be to the point where you find the exit. So here are the dimensions of this exit pipe, we have the radius equal to, the radius is given as 20, that is, the radius is 1 times 10, it is 1 millimeter, which is 1 times 10 power minus 4, I think, power minus 3 of a meter. And we know the length of course should be the length here is 20 centimeters, which is of course 2 times 10 power minus 1 meters. And so we apply the Poiseuille's, consider using the Poiseuille's formula. The formula relates the velocity, the volume being equal to, of course, T is the volumetric rate, equal to pi times change in pressure times the radius raised by 4 divided by 8 times the coefficient of viscosity times the length. This is the Poiseuille's formula. So we are going to use this formula, where this is, as we stated, this is the volumetric rate, which means it is the volume per second, volume per time, and so recall we know that let me just write it here, where delta P is equal to, for this case, mgh. It is the density rho gh. So if we substitute back the delta P, we are going to have pi rho gh r power 4 divided by 8 eta times L. And from there we can determine the height h. And making h the subject, if we make h the subject, we'll be having h equal to 8 eta L times V, the volumetric rate, divided by pi rho r power 4. We can simply substitute and have it is 8 times 1.5. Remember, V is equal to 1.5, it is centimeter power 3, the centimeter cubed per second. So I have that one times 10 power minus 2. Of course, this is just to transform this one to transform the 1.5 centimeter cubed to meter cubed, we have that one, then times 10 power minus 3. The 10 power minus 3 is simply the radius, the radius. No, the radius is down here, so this one is times 10 power minus 3. This one, okay. Let me check this. Times 10 power minus 3, see. This is 10 centimeter cube times 10 power minus 3, it's okay. Times 2 times 10 power minus 1 divided by pi times the density, which is taken 1,000, the density of water, times 9.8 times 1 times 10 power minus 3 power 4. Okay, so half, this is h, the volumetric rate, times 10 power minus 3, equals that. Okay, the value that you will be getting, just check if you have that, and should be 0.078 meters. 0.078 meters. Okay. Let's see question number 1, question number 1, part C. Question number 1, part C, that is that. Here we have just substituted 8, which is this. We have 1.5 times this, which is, okay, this one is the, let me just show it clearly. This one is the 8, is okay. This one here is the volumetric rate, 1.5, which is converted to the meter cubed, the cubic meter. And this one takes the eta, which is the coefficient of viscosity, which of course you are given as the useful information on the front page of your question, the question paper, which of course shows that the coefficient of viscosity of water equals to 1 times 10 power minus 3 Newton second per meter squared. So this takes the value for the coefficient of viscosity, and this is the length, which is of course this one, the length 2 times 10 power minus 2. So it's now okay. That's where you get finally get that result. Part C, Roman 1, the question asks, explain why machine parts are jammed during winter. You are required to explain why machine parts usually jam during winter. The idea is that usually the machine parts are lubricated or they are greased, and usually grease, the viscosity of grease is a function of temperature. So when the temperature increases, usually the viscosity decreases, and you can testify this one by considering honey, for example. If you have honey in a container and you have it warmed, usually it becomes less viscous than the case when honey is cold. So the same applies to such machine parts which are greased. So when temperature increases, the viscosity of the grease usually decreases, and so it's like they can easily move against one another. But when the temperature is low, the grease, the viscosity of grease decreases, and when the viscosity decreases, it becomes hard for the two parts to be, interacting parts to move against one another, and so they can easily jam. They can easily get jammed. So to put it in summarized writing, that is part C, Roman 1, is that during winter, the temperature is low, and as a result, engine oil which of course could take the place of grease, the one I have been explaining, and the engine oil behaves the same. Likewise, if it gets cold, the viscosity decreases, and if the viscosity decreases, then the movement becomes hard. And so engine oil or grease between the two parts, grease, I don't know, grease, I think it is written this way, grease. You will just correct me if I've written it not very correctly. The grease becomes more viscous in this sense. So the engine oil or the grease has a high viscosity. Let me repeat to emphasize. We said if honey is warm, it means its viscosity goes low. If honey is cold, its viscosity goes high.
So for this case, look at this. If the temperature is low, the viscosity is high. It means it is more viscous, more heavy. If, I think I have made the analog very clear. I want just to make an analog of honey and the engine oil. So if the temperature relative to honey, if the temperature is high, the thing becomes less viscous. Yes, which means the viscosity goes low. But if temperature goes low, the viscosity will be high, just as this case. The engine oil, if the temperature is low, the viscosity is high. It means the oil will be more viscous, which means it is very hard to for the parts to move against one another, and therefore they can easily be jammed. The second part of the question, that is Roman 2, reads, Roman 2 reads, a cylindrical tank with large diameter is filled with water to a depth D equals to, let me just sketch the tank just as I did the first case. Let me just also consider there is an exit, and the tank is filled with water to a depth of, I just think of the depth from here to here is 0.3 meters, and a hole of cross-sectional area of A, I'm just thinking just this one to be a hole. This hole has a cross-sectional area of 6.5 centimeters squared. In the bottom, of course, it is somewhere at the bottom, around the bottom of the tank, and it allows water to drain out. What is the drainage rate? You are required to determine the drainage rate. Here, the best approach to respond to this one will start with the Bernoulli's principle, and so the Bernoulli's equation is written as, for this case, we consider somewhere where the height, to the point to which the tank is filled, say a height h, and so at this point, say, we'll be saying 0.1 to be 0.1, and then we'll be having 0.2 here. This was the diameter, so it is diameter. The diameter, the whole cross-sectional area. This is the area, cross-sectional area. Okay. And so we are the Bernoulli's equation, the Bernoulli's equation can be written as P1 is equal to P1 plus a half rho V1 squared plus rho GH1 will be equal to P2 plus a half rho V2 squared plus rho GH2. Okay, we are sure this point, of course we are not told this tank is covered, and so we just assume it is not covered, so that the top part is exposed to the atmosphere, and also the orifice, the point at which water is getting drained, is exposed to the atmosphere, and therefore the pressure at point 1 will be equal to pressure at point 2. P1 will be equal to P2. And if because we are sure that the velocity of water leaving the tank will be very high compared to the velocity with which the water in the big tank is moving, and so we can think of we can assume that the velocity for the water in the big tank, velocity V1, will be equal to approximately 0, very small. The velocity will be very small, and if we take that assumption, then we can rewrite our equation as rho GH1 is equal to a half rho V2 squared plus rho GH2. And having that written, we can make V the subject, V2 for that case, equal to rho GH1. I can take H1 minus H2. H1 minus H2. Then of course I have to multiply, because I'm divided, I have to multiply, and of course the rho gets off, because there is rho here and rho here. I can just cancel them, so that I'll be having the two times G, and then finally of course I'll be having the root. So V2 will be equal to the root of 2GH1 minus H2. H1 minus H2. And remember, this could be considered as the H2, the height to which the hole is made, and then this other one from that point to that other point, that is the H1. So H1 minus H2 will simply give us 0.3, where H1 minus H2 is equal to 0.3 meters. And so, substituting all the values, we are getting V2 is equal to root of 2 times G 9.8 times 0.3 meters. The result of this is 2.42 meters per second. That is the velocity at this point, the velocity V2 with which the water is getting drained out of the tank. Now the question asked us to determine the rate at which the water is being drained. The rate is let me call it Q, the rate for this point at which water is getting drained will be V, the velocity at that point, times the cross section at that point. That will give us the rate. And so if you substitute 6.5 that we are given, we just change it to meters. We have power 4 meters squared, then times the velocity, that is 2.42 meters. If you compute, you are going to get 1.6 times 10 times, let me write it here, 1.6 times 10 power minus 3 meters cubed per second. And we were asked to write the answer in meters cubed. So that will be the case. Just 1 minute. Then finally, we were asked to compute the distance below which the tank will have the cross-sectional area equal to 1/2 the area of the hole. Here you will just use the same from the equation. Of course, we shall consider another point where we will call it point 3. And so if we have point 3, it means we'll be having 1/2 rho V2 squared plus rho GH2 equal to 1/2 rho V3 squared plus rho GH3, relating our point and the point which is assumed. And so what we are required to determine is similar to the H1 minus H2. We are required to determine H2 minus H3. And so we can make it the subject from here, since we are given that wait a minute, this is we are given that the velocity, no, wait a minute, here we will use a different let's get first the volume. We have to use the continuity equation relating area A1 and velocity. For this case, we will have to consider the third point, assume it to be anywhere, say at this point number 3. So we'll be having the area and equate it with the point that we know, the volume, the velocity and area, and so we can determine the velocity V3. After we know the velocity V3, then we shall apply the Bernoulli's equation by writing 1/2 rho V3 squared plus rho GH3 is equal to 1/2 rho V2 squared plus rho GH2. So since we have already determined V3 from this equation, we will substitute V3 here and finally determine the difference between H2 and H3. We shall finish up this part next time.